we totally messed up.
You go do a lecture over there.
Yeah, let's go there.
Princeton has a lot of money, right? To buy all of us.
Exactly. Yeah, when good's the money sitting in the bank?
That's right, yeah. There you go. And we can go there next.
That's right. Well, this is a day's walk from the other house. Actually, we got there that night. That was the next one.
So where is this?
In the Sierras in California. Trip that's 250 miles or something. So my two sons and I did it in 1999.
Is it along the Pacific Crest Trail?
Yeah, it's the John Muir Trail. Yeah. Oh, is it? Could be. Yeah, that's sort of, this is Thousand Island Lake and that sort of thing. Famous picture.
So how long did it take you?
So my younger son had just turned 13.
Okay.
So I decided we were gonna do about 10 miles a day and not try and do more than that. And it worked out great. So we spent 3 weeks.
Nice.
We had a layover day in the middle. This is the Andes on the top of Mount Whitney. It was a good trip. They're nice.
Yeah. So how do you explain that and how entropy is a mechanism? If you have a global system, it might need a local observer to come alive and give them a global.
So thank you all for sticking around to the last lecture. It's been a long week. Our last speaker is also the first speaker, Professor Steve Lyon, who will be talking about donor-bound electrons being qubits in silicon and electrons floating those with helium. Yep,
I think that's it.
Good.
I hope that's it. So yeah, you all thought this was about quantum computing. It's a psychology experiment to see how many were here on the first day and also at the very beginning and very end. So I'm not quite sure I know how I got to be at the two ends, but I did. Just lucky, I guess. Okay. So yeah, so I'm going to talk about electron spin qubits, and one of the things I'm gonna try and answer. There were some questions for Jason, right? He does electron spin qubits too, and the question was, why not donors? And I'm going to tell you about donors, and also some of the problems with donors, some of the good things, some of the bad things. It's always a mixed bag. There's no simple answer, and basically what Jason said, the fact that they're really, really small is probably the single biggest problem that they have. So by way of outline, I'm going to talk about donors. I'll say a little more about spin coherence in silicon and some about silicon donor experiments. And then I'm going to talk about some other schemes. I'm going to show, people have a bunch of ideas about how to get around the problems with silicon donors. And then I've been interested with a scheme that plays with electrons floating on helium, and I'll talk about that. So one thing that I mentioned on the very first day, the question is, why do you want to do electron spin qubits? And fundamentally, there's one answer. They're really small. All right? And so if you want to make, and I mentioned this, if you want to make a full-scale, great big quantum computer, right? You want to do machine learning in some big problem, or the problem people like to use as sort of a benchmark is factoring, because the algorithm's very well defined, you know exactly what you want to do. But basically, you need something like 10 to the 4 qubits. That'd be a big computer. All right, Andrew Hout talked about surface codes, which are one of the favorite ways of doing error correction. You end up with 10 to the 9 physical qubits. Now that's assuming you have a surface code with nearest neighbor interactions only. All right? And these guys there was a bunch of press about it. It's a usual thing. You publish in one of these, sort of National Enquirer type journals that you get in your grocery store, and they have all the press releases and things like that and try and make a big deal about it, and everybody says, oh, every other week somebody has solved the problem of quantum computing. Well, the poor guys who wrote the paper, you get very embarrassed by all of that, I can say. But at any rate, if you take their model, so they said, okay, let's do a surface code with trapped ions, and we're gonna have 10 to the 9 qubits, and we're gonna figure out how big we need it. And it turned out to be something like 100 by 100 meters, and to put it in units I'm used to, that's 2.5 acres. All right, so that is 5 times the size of the plot of land my house sits on, right? And this is an ultra-high vacuum system, all at 4 Kelvin. It's kind of big, all right? Okay, well, it turns out life isn't quite that bad. Real trapped ions, you can move them around. And it's low decoherence, and you can save sort of a factor of 50, maybe 100, something like that. So now you get down to 10 by 10 square meters. So you need sort of an ultra-high vacuum system cooled to 4 Kelvin that's sort of half the size of this room or something. All right? So it's still kind of big. What about if you're doing superconducting qubits, right? Andrew Houck talked all about superconducting qubits. Well, his are resonator-based, and the resonators, right, you have microwaves, right? They're 5 gigahertz. They have a wavelength like that. Okay, well, you can pack them on, but basically every resonator is going to take something of order 5 square millimeters. And in a very simple-minded picture, you're going to need 10 to the 9 of these. You can't move resonators. And so you're back up to 2.5 acres. Well, there are a lot of clever people working in that business, and they figure they may be able to store of order 100 photons in a resonator and keep them all distinct. And now you're back to about 10 by 10 square meters. Now, with the ion traps, it basically has to be a single flat surface. With the superconducting resonators, you can imagine, hey, all I have to do is run wires so I can stack them. I can make, 100 layers, each one only 1 meter square. All right? But okay, so now you need a fridge that can handle a 1 meter square thing and it's 100 layers thick. Yeah, okay. People are going to build those. I'm sure there are people working on it right now. I know right now you can get a fridge with a base plate about that big. Right? Dilution refrigerator that can get you down to about 10 millikelvin. Electron spin qubits, on the other hand, right? You looked at those quantum dots that Jason was showing? You can do a qubit, it's like 1 by 1 micron. All right, and if I stick that in, I can make my 10 to the 9 qubits, it's 10 square centimeters, right? That is a lot easier than 2.5 acres. They can also be very fast, right? You can get those up in the gigahertz range. So, at least in principle, spin qubits can be small and fast, and that would be good. Of course, life is never that simple. So one of the spin qubits is what was brought up, is using a donor. Let's take a donor atom, right? And so a donor, and this is the PowerPoint version of a silicon crystal, right? By definition, it becomes two-dimensional. Okay, what we're doing is just substituting a phosphorus instead of one of the silicons. You make all your your bonds with all the silicon, but there's one extra electron hanging around. Its ionization energy is about 50 millielectron volts to take this electron and let it run freely through the crystal. Here is sort of an energy level structure. It's sort of like a hydrogen atom, except Jason mentioned that silicon is a little more complicated in the vacuum. It has these valleys. And so in fact, your ground state, your 1s state, is split, but there's a state down here that is the only degeneracy is spin, and it's about, in phosphorus, about 10 millielectron volts away from that state. And it turns out the nucleus is a spin 1/2. Phosphorus only comes in that flavor. And so you can make a qubit like that. So Jason mentioned that Mike Thewalt had gotten, 39 minutes, or at low temperature, he had a 3-hour nuclear spin coherence, and he was looking at that phosphorus nucleus. In order to get that, you have to pull the electron away. The electron otherwise will decohere the nucleus. So, Jason had showed pictures of these papers from Daniel Loss and David DiVincenzo showing quantum dots and sort of theorist view of quantum dots. Well, the same year, 1998, Bruce Kane came up, published a scheme using donors in silicon. All right, and the basic picture is this. He is going to have a hunk of silicon down here, probably silicon dioxide there, and a bunch of gates. And then under the, what he called the A gates, he's going to put a phosphorus atom under each one of those with an electron. And the way his picture worked is that these A gates, and it's called A because A is often used to represent the hyperfine interaction. And so this is going to modulate that. He figures, well, normally these dots represent the electron wave function around the silicon, around the phosphorus. Normally, that's sort of centered on the phosphorus. Well, he's going to put a positive bias on there, pull the electron away, and because that, it changes the hyperfine interaction with the phosphorus nucleus and changes the frequency, the spin resonance frequency. And the idea is, well, what I can do now is I can put a voltage on there and I can say, well, that one, and that one, I'm going to tune them into resonance with my microwaves, and I'll send a microwave pulse to everyone, and that way I can select which guy gets affected by this. Then the idea is there are these so-called J gates, and right, J comes from the fact that that's often used to represent exchange interaction. Well, what you do is you use your A gates, pull the electron up against that surface, and then make that J gate positive, and get those two electron wave functions to interact, to overlap, and get an exchange interaction, and that gives you a 2-qubit operation. So that's the idea. I should say, and I'll show some of the things, these are all very hard, all right? And Bruce knew that when he did this. This was just sort of... So first, I'm going to say a little bit more about spin coherence. In, say, 2000, actually 1998, when Bruce proposed that, the assumption was that the electron spin coherence of an electron bound to a donor would be maybe a millisecond. And that came from some experiments that were done by Jim Gordon in 1958. So Jim Gordon was a graduate student who made the first maser, and he then went to Bell Labs, and he wanted to make a phosphorus-doped silicon maser because George Fayer had done a whole bunch of spin resonance measurements on phosphorus-doped silicon, and George had a piece that was isotopically enriched, not super well, but pretty good. And Jim measured, in fact, he did the first ever microwave spin echo experiment on electrons, and he measured about 0.5 millisecond for the coherence for T2, which as far as I know was the longest coherence ever measured until people started measuring phosphorus-doped silicon again after 2000. But at any rate, if you look at this was a table that David DiVincenzo had written up, and basically the assumption was electron spins might get to a coherence of about 1 millisecond, sort of because they could do that. I should say Fayer had measured T1 flip time, and he knew that was several thousand seconds, but you needed to do echoes for T2. Well, so as Jason mentioned, okay, people started measuring this more carefully when people got interested in using these as qubits, and Jim had a piece that was doped about 10 to the 16 phosphorus per cubic centimeter, and you get a piece of isotopically enriched silicon, and this is just as a function of temperature, and in fact, what I really should have done is plot this on an Arrhenius plot, because this is just an e to the minus e over kt, and the delta E is at 10 millivolts to the first excited state. But at any rate, and if you measure a piece doped 10 to the 16, you get just about the same number that Jim got. But now if you measure one that's doped 10 to the 15, it's longer, and 10 to the 14, it's longer, and 10 to the 12, you're up here of order a second. And then what you can do is, what's going on is you're getting interactions between the dipole moment of this electron and the dipole moment of that electron. And by lowering the density as we move those things farther apart, those interactions get weaker. And there are tricks you can play in a spin resonance experiment to further reduce the effect of those interactions. And in fact, if you go through all of this, you can get up to around 10 seconds. Or at least that's as long as anyone's gotten so far. If you look, everybody likes to make these charts, sort of like the charts that people like to make of, you know, how big a transistor is or something. So everybody likes to make these charts. Basically, what has changed over the years are two things. One, the material, and this is a big issue, the material is improved from being more heavily doped with about 1,000 ppm silicon-29, which you need to get rid of these nuclear spins. And this one, actually, I think this may have been really about 50 ppm, and much more chemically much cleaner. And then also, there are different sort of physical processes going on, and people over the years learned what all these things are. And over here, it's called instantaneous diffusion. And then there's a regime where they're just donor flips and donor flip-flops and things like that that limit the coherence. But in the end, you get something like that. You'd be limited to this 2,000 seconds, but we're not close to that yet. There are tricks you can play. So you play the same tricks that the ion trap guys do. So when you want to make an atomic clock, you use what are called clock transitions. And what a clock transition is you get a hyperfine coupled system. So the electron and the nuclear spin couple such that there is a range of magnetic fields where your frequency of that transition is independent of magnetic field. And bismuth does that very nicely in silicon. And so we, in fact, have measured some up around that 7 gigahertz clock transition. And there you don't have to do any extrapolation games or any of the other stuff. You can have a more heavily doped sample so you get more signal. And this shows just a straightforward Hahn echo, so a pi over 2 pulse and a pi pulse, and you get about 2.5 seconds. And actually, we've done others where you can get longer. And it just comes from the fact, because you're sitting at this particular frequency at that clock transition, you're insensitive to any fluctuations in the magnetic field, like from the other donors or from the silicon-29s, and you can just get yourself a long coherence. So, what is the limit for this coherence? And I think the simple answer is we don't know. At this point, we're still being limited. Well, there's residual silicon-29, though the bismuth makes that, if you go to the clock transition, that probably limits you in the few 100-second range. Donor-donor interactions are still a big deal. In most architectures that people are now thinking about for donors, we would have those donors fairly far apart, and the interactions between the donors would be negligible. So we could get T2 well above 10 seconds. But do we need it longer? Okay, one argument is bigger is always better. It's not so clear that applies. The thing is, there are many other effects. When you start making devices, right? Now you have to put down gates and all these things to control what's going on. Surfaces, you have to be up close to a surface or an interface. You have gates and gate voltages and all that is almost certainly going to be more important than whatever background decoherence you have coming from the silicon.
A question?
Yes.
For realistic applications, we would expect our spins can be operated for example, the half pi Rabi pulse. Then we would flip them at the same point. But is it T2 star better measures the coherence than T2?
I'll address that. So in some ways, T2 star may be a better measure in the sense that, well, I'll come back to it, but like this surface code, if all your spins were exactly the same frequency, that's great. But if they're slightly different frequencies, your surface code will automatically sort of correct for that, as long as they aren't too far off. And I'll come back and talk about exactly that issue. One of the arguments for donors has been, this is essentially, I mean, we think of it like an atom. And we know all the atoms have exactly the same frequency. And so we imagine all the donors have exactly the same frequency. And if we do that, we're making a mistake. They don't have exactly the same. And I'll come back and talk about exactly that problem. You might say, well, okay, Jason, he was talking about all these electrons in quantum dots. Why was he always putting them in quantum dots? And this is the answer. The problem is that if your electron is free to run around, so here are measurements of spin echoes from just 2D electron gases. This is in silicon. So might imagine, okay, we should have long coherence. This is T1. T1 is about 2 microseconds. T2 is about 3 microseconds. It's a rather odd situation where T2 is longer than T1. Doesn't happen very often in the spin world. Where this comes from, we believe, is, well, first off, T2 greater than T1 says there's something anisotropic going on in the way this relaxation occurs. And just sort of abstractly, we can think of the things that drive T1 and T2 as some fluctuating magnetic fields. And it appears from the experiments that what's going on is you get this so-called Rashba effect that Jason mentioned. What that is, it's a spin-orbit interaction that wouldn't be there in the bulk, but now we've broken the symmetry. We had silicon here, and now all of a sudden we go to silicon germanium. We've broken that symmetry. And what you end up getting is an effective magnetic field that is perpendicular to the motion of the electron. Always stays perpendicular. Remember, Jason had those pictures of those arrows going around the circles. Well, what that means is as these electrons go along and they scatter, right? They have some mobility. This happened to be, those experiments were at the time the highest mobility samples that existed. This is a fluctuating magnetic field, but it's always in the plane. And so if your magnetic field is perpendicular to the plane and the fluctuating magnetic field is always in the plane, it's always perpendicular, so it always causes spin flips. And that's what gave us that T1 and T2. If we put it in the plane, if we did the experiments where we put the magnetic field in the plane, and then T1 gets longer, but T2 gets shorter. And you can fit this, if you put in the mobility, the sort of characteristic time between scattering events is about 10 picoseconds. And these in-plane fields are about 10 Gauss. And there's an effective out-of-plane field about 5 Gauss. So by way of comparison, right, often experiments are done up around a Tesla, which is 10,000 Gauss. So these are small. Gallium arsenide, these come from spin orbit. They would be 3 orders of magnitude larger. But they're still enough to cause coherence issues. So you can't just let these guys hang out freely. If you confine them in a quantum dot, now they're not scattering around like that. They don't see that. So this process goes away, and that's why Jason can get long coherence in a dot. So let me just very quickly go through this. Jason already talked about it, and in fact, the first day I talked a little bit about Cooper pair boxes. Well, this is a Cooper pair box, but without the Cooper pairs. They're normal metals, and so they're just electron boxes. And this is a single electron transistor that Jason talked about. And in fact, it looks like we stole the same, he had the same sort of blue color scheme. I think we must have stolen it from Susan Angus. But at any rate, the idea is that you have, in this case, these are all gates sitting upon silicon dioxide. And so what's going on is actually down in the silicon. There are electrons that are pulled up to the interface between the silicon and that blue layer of silicon dioxide. And this is the island here. And what's going to happen then is electrons from this 2-deg may or may not be able to tunnel through that island. And this island can be very small. In this particular case, right, that's 200 nanometers. So that's well below 100 nanometers is this island. And so just the capacitance is small, so the charging energy is large. And if this is your energy level, no current flows. Now, if I vary that plunger up at the top, I can vary the energies. I can bring that into resonance, now current flows. But if I go farther, then the current shuts off again. And then you can repeat this. You get it, you do it again, and it's periodic. And so these now little peaks in current tell you are basically counting electrons here, but it's also very, very sensitive. It's just a transistor that's extremely sensitive, very high gain transistor. That's all it really amounts to. And so now what Andrea Morello's group in Sydney did, they said, okay, what we're going to do is we're going to implant some donors right next to this SET, right under that plunger gate. And they're going to put in a bunch of them with just the idea one will have about the right tunneling coefficients to work, and it turns out that's true. And now it's exactly what Jason was talking about. What they're going to do is put this in a field of a Tesla or a Tesla and a half. It's going to split, spin up and spin down. They're going to bias it so that that island energy is here. And if it's the high energy state, then that electron can jump off and go into the island. If it's in the low energy state, it can't. So if it's in the low energy state, nothing happens. If it's in the high energy state, that guy can jump off, get into the island. Now the island is not one electron. There's probably a puddle of several hundred. And they're going to be spin up and spin down. And so you'll jump off, and that's going to change the current. But then one of the other ones, a spin down electron, is going to jump in and shut off the current. And it's exactly what Jason was talking about this morning. And what you then see is a jump in the current that then turns off. That's on a 200 microsecond. And so the business of the dozen donors, it's just a matter of picking the donor that has a convenient tunneling matrix element such that you tunnel and you get a peak that's a reasonable length of time that you can see easily, just exactly what Jason was talking about. So you can do that. And they did that, and they could use that to measure T1, how long it takes a spin to flip. They were in a field, I think in this experiment, maybe 1.5 or 2 Tesla. And remember, Jason showed that the T1 decreases as a relatively high power of the magnetic field. It's a little different in silicon because you don't have the piezoelectric phonon. So the numbers come in, I think it's beta the 4th, if I remember. End result, though, is, yeah, 6 seconds is reasonable. But now what you can do is, remember Jason was talking about, well, you can do the sort of brute force spin resonance experiment, and that's what they did. This is a shorted transmission line that they can put current through here, microwave current, and so they can drive this spin to flip. And here they can show what they can do now is, you know, you apply it for a certain time, and then you measure, and you keep doing that, you reset, you keep doing that, and you can trace out these Rabi oscillations. The results are they can get what's called T2 star. That just means you don't do the spin echo. You take a spin, you start it and spin up, you put it into the plane of the Bloch sphere, into the equatorial plane, and then later on you're going to tip it back. Now you can, as long as the spin, if you timed it just right, and the spin came back to exactly there, then it would flip up and you'd get it. On the other hand, if the spin's frequency is a little off, it might be pointing over here and it doesn't flip all the way up. And so that's what T2 star measures, and it's telling you something about how the, in some sense, the disorder, and in fact what it's going to do is going to tell us how different are spin frequencies from one donor to the next. But then you can do this Hahn echo, you can do this 2-pulse echo, and you get about a millisecond. This is, by the way, an isotopically enriched, so this is silicon-28. And then what you can do is you can keep flipping the spin back and forth. And the idea there is that now whatever noise only has a little while to act on the spin, because then you flip it, and now that everything gets reversed, and so you can filter out noise, and they can get up to about a half a second. And you can also play with the nuclear spin. You can take your qubit, the spin and the electron, transfer it to the nucleus by doing a couple microwave pulses, using the hyperfine interaction, and the nuclear spin would stay coherent for like 35 seconds. So half a second is a single donor spin coherence. So now I said I would tell you some of the difficulties that you run into with silicon donor qubits. First off, you remember there were these A gates that we were supposed to start tune the spin frequency. Well, it turns out it doesn't tune very well. And you need high voltages. You'd like to be able to tune it megahertz because you want to be able to give it fast pulses, right? You want to be able to do fast operations. And so if you only tune it 10 kilohertz away, well, you have to do really slow pulses so the line width of your pulse is within 10 kilohertz. And it's hard to get high enough fields to do that. The other thing is these J gates, you're talking about, well, I want the electron wave functions to overlap. Well, these electron wave functions are only 2 nanometers, all right? And people are pretty good at lithography, but they aren't that good, right? 2 nanometers is still just too small, right? You're talking about putting 3 gates into 2 nanometers. That's just too hard. Another thing, and I'll show just a picture, they're these so-called donor exchange oscillations. Actually, let me just jump forward to that. I just stuck that in. The problem is there are these multiple valleys in silicon conduction band. And what that means is, oh, it cut off, I'm sorry. This is the distance between the donors. And basically, you get these valleys and peaks and valleys and peaks, and that corresponds to moving at 1 lattice constant, right? Of that order. Now, this was a paper that was calculating, there's one approximation that gives you huge sort of peak to valley ratios. Well, it's not really that bad. You can do a fancier calculation, but still you're getting this exchange oscillation. Here was actually another one that was a little, the green one was a great big huge numerical calculation. The point is that you put in 2 donors and you would like to say, well, I'm going to put this voltage on and I'm going to get it this exchange. Well, in fact, things vary all around and no 2 will be the same. And so that all comes from the fact that you have multiple valleys in the silicon conduction band. And I guess the last one is, if you're going to put donors into the silicon, you remember Jason, he used silicon-silicon germanium heterostructures. And you do that because they have very high mobility. There isn't a lot of scattering. You can get those with a mobility, I think the highest people have reported is about 1.5 million. Centimeters squared per volt second is the standard sort of units. However, the way you usually put in donors is by ion implantation. And now the problem is, you don't know exactly where that ion's going to end up, and you have this little narrow 100 angstrom thick silicon quantum well, and you have to hit it, and you can't do that. And if that phosphorus ends up in the silicon germanium, its electron jumps off and ends up in the quantum well because you're modulation doping. And now you have all these extra electrons around that you don't want. So it's very hard to position your donors. So you probably need sort of metal oxide semiconductor, the usual things that the semiconductor industry uses. But now, yeah, you're probably limited to a mobility of maybe 20,000 or something like that. There's just a lot more disorder at the interface. And so how big a problem that's going to be right now, we're not sure. I'll say a little more about it. And then this gets back to this question of T2 and T2 star and all. Right, we would like to assume every donor is exactly the same, and so the spin energy, the frequency is exactly the same. And when Chris Monroe uses ions, his frequencies are exactly the same to within like a few hertz. On the other hand, how good do you need? Well, if you have a surface code, right? You remember you have to do a series of, gates and measurements and gates, and you go around these plaquettes. And if you assume one cycle takes about a microsecond, and you say, well, I can't have a phase error that's bigger than about 0.1%, which is what people typically use for the surface code, that means I don't want more than 2 × 10⁻³ pi, and the maximum line width I can have is about a kilohertz. It's just saying I can't have more than 10⁻³ cycles in a microsecond. I need a kilohertz line width. Well, the very best isotopically enriched silicon that we've gotten our hands on, which comes from this Avogadro project, Jason showed the pictures, right? The Avogadro project was all about how to make a standard kilogram. And the idea was make a perfect sphere of isotopically enriched, chemically pure silicon, polish it into a perfect sphere. Now you can measure its diameter interferometrically, so you know exactly how many atoms there are in there. You know that every one of them is exactly mass 28, and now you have a new standard kilogram. It didn't exactly work the first time. Apparently what happened, so it's a fun story because how do you polish something that perfectly? You get the lens polisher who lives in Australia now, and he actually can polish things to a few nanometers by hand. He can feel a few nanometers. So you can check it. You can go measure it interferometrically and see, is it really round? It is. The only problem is apparently somehow during the polishing, I think it was some manganese diffused into the silicon. That's not good because that changes the mass. So now they're making a whole new, or they plan to make a new pair of those spheres. The only problem is that crystal polisher, that lens polisher, is now in his late 70s, and he has never trained anyone to be able to do it. They claim, on the other hand, that diamond turning machines are now accurate enough to do it. I don't know. But they're trying to build a whole new set that won't have something diffused in. So there's the good news for us is that when you pull a crystal of silicon like that, you make basically a cylinder. And now you cut it and you make spheres. Well, when you cut it, there are corners that come off. And we get our hands on the corners. And that's how we do experiments. So at any rate, very best material in the bulk, we can get a few tens of kilohertz, and we're not exactly sure what's limiting that. I think I figured we're getting about 30 kilohertz line width. On the other hand, what people usually like to do is, Jason was saying, instead of having a whole wafer of pure 28 silicon, you have natural silicon, and then you grow a little epitaxial layer of 28 silicon on top of that. The only trouble is they have a different lattice constant. Now you say, how can silicon and silicon have a different lattice constant? Well, one has 5% silicon 29 and a little bit of silicon 30, and they have this different 0-point energy and 0-point motion. And that causes a difference in lattice constant at about the 6th decimal place. So people have measured it. And what that does, though, is introduce strain. And that gives us our line width, the best we can get is a couple hundred kilohertz. And we have to individually tune every one of these qubits to set them to the same. I mean, for experiments you do in a university, no problem. You're going to have 5 of these and you tune them up, no problem at all. But now if some guy wants to build a big quantum computer and he has 10 to the 9, that may be a little hard. In addition, local strains. I mean, you just grow silicon dioxide and you have localized strain. Or gate metals. It's well known. You have an aluminum gate. Okay, all is good. You cool it down. Aluminum and silicon have a different coefficient of expansion. At low temperature where you're going to work, it introduces a lot of strain. Probably this corresponds. There are people have been talking about using silicon on insulator. When we've measured that, the strain is a huge inhomogeneous strain. So, it's not easy. Defects. Well, do we care? Thermodynamics says we're going to have some. This shows some measurements. So people are used to measuring defects at silicon dioxide interfaces, but the scale that they typically use is 1 eV. Well, this is 0 to 10 millielectron volts below the conduction band edge. And actually there are 2 different samples here. This little point X is the density of states for a single subband in a 2D system. And one sample just came down exponentially. We think it's probably the band tails because you have this amorphous material on top of your crystal, and we think that's probably the band tails. Another one had that, and that we think, I am betting this is sodium impurities in there. The problem is, if they're more than a couple millivolts deep, and now you put gates on there, you can't dislodge those electrons. You can't put on a big enough field to get rid of them. And so you're going to have, of order 10 to the 10, that's every 100 nanometers. You're going to, on average, you're going to have these. They're going to be spread all around. They're going to distort your dot energies. Maybe this is just a calibration issue. I don't know. You have these extra trapped electrons. So if you have your dot here and there's an electron here, you can have an exchange interaction between those 2. Or if you're, say, trying to move an electron from one dot, you know, Jason has 10 dots in a row or 9 dots in a row, and you want to move an electron from one to the other. Well, if there's a trapped electron, as you go by, it might exchange. It may also mess up some of the microwave coupling, right? These things move. They absorb microwaves. So, life is not real simple. On the other hand, people have done some really neat experiments. So I showed the experiments with the measuring spin resonance of a single donor. People have tried doing the experiments with 2 donors, and you can see donors that are coupled together, but you don't have enough control. But there's a group at Sandia that did a real neat experiment where they used a donor and a quantum dot. And what they could do is they actually had 4 electrons in here. And the reason they had 4 is exactly this business that Jason was talking about, the valleys. What they did at the interface there, you end up with 2 valleys and 2 spins, right? The other valleys get pushed away out of the energy range, but you end up with 2 valleys and 2 spins. And so what they could do is they could fill up the lower 2 states with a couple electrons, and then they only have to deal with 2 at the top. And what they could do is they could take an electron and they could either put it onto the donor here, or they could pull it away and keep it in the quantum dot. And I had hoped Jason was going to talk about singlet triplet qubits, which was one of the things he invented, but it was a dozen years ago, so he's probably bored with that by now. But the idea is that I can have a qubit not with 1 spin, but made up of 2. And one state is they're in the triplet state, and the other is they're in a singlet state, right? So all you're doing is you have up, down, plus down, up is the triplet, up, down, minus down, up is the singlet. This is one of those states I talked about the very first day. They have exactly the same energy. So they're independent of magnetic field, so they protect you against magnetic field variations. But at any rate, what these guys do is they make a qubit where the singlet is at the top, the triplet is the bottom, and they can use the hyperfine interaction of the nuclear spin of the phosphorus with that electron to drive them around on the surface of this block sphere, so they can use rotate between the singlet and triplet with the electron on the donor, and if they take the electron off the donor, you have an exchange interaction between those two electrons, and so you can drive yourself anywhere on a block sphere with that. So they had a very clever arrangement. This is their scheme. What they did was they implanted a bunch of donors, 10 or 15, and found one that worked very well. All right? Now, these are their exchange oscillations. Okay, the data is in blue, the fit is in red. These are experiments. This is not an engineered product at this point. One thing people often worry about is they say, oh, well, silicon, the effective mass is large, therefore it has to be real small. Not really. This is a silicon quantum dot. Actually, this picture came from Mark Erickson at the University of Wisconsin. This is a static random access memory made by IBM some years ago. This was a 32 nanometer process. Now everybody's at 14 nanometer. These things are a lot smaller than that. So if we can figure out the physics, there are people who know how to make things small enough. That's not the issue. So, as I said, there are a couple problems. One, the line width is large. One is that you have to try and get these donors so close together, and that is probably the one that is hardest to solve. And a bunch of people have come up with schemes to try and get around that. These are ones I know about. This one I know about well because it's ours. What we want to do is we want to put bismuth donors down here, and then what we want to do is have quantum, these sort of large gates represent quantum dots. And we want to be able to do exchange interactions with the donors and then move the electron. Now you remember I said, well, moving electrons is bad because they decohere. But if you move them 1 micron, right? Electrons typically in a semiconductor, sort of a slow speed is 10 to the 6 centimeters per second. If you have to move 1 micron, that takes you what, a nanosecond? Picoseconds? Picoseconds, yeah. You don't get much decoherence. So as long as you don't move it very far. And so you can do some things like that. There's the Andrea Morello's group in Australia at the University of New South Wales. What they want to do is this business of taking an electron and using a dot above it to pull the electron partially off the donor. And if you pull it partially off, right, there's an electric dipole moment. That electron can move back and forth in this direction. And what they have argued is that if they get it right at the spot where it's sort of half and half, a bunch of the decoherence goes away. And so they believe then they can get 2 of these donors to interact through the electric dipole field rather than in a magnetic dipole field. And again, you can move donors a micron away or something like that. There's a group in Simon Fraser. So Stephanie Simmons, her approach is saying, hey, let's go to very deep donors. They're donors like sulfur that can be put in, have energies half of the band gap, so they bind with half an EV. But they're optical transitions on those donors of sort of half EV energies. And she wants to try and couple these donors through the optics. And now what you would do is you would build some sort of photonic band gap thing and move your photons around. And Michelle Simmons, if your name is Simmons, do not go into this field. There is a Michelle Simmons, a Stephanie Simmons, and Wisconsin, another woman named Simmons, and I can't remember her name. She moved out. She went off and started working on energy things. But Steph and Michelle are still both in this field and trying to keep track of who is. But anyway, so Michelle is in New South Wales. What she knows how to do is to place donors one at a time with a scanning tunneling microscope. And so she can go in and put these donors in there. They still think that trying to put them close enough together to do an exchange interaction would be hard, but they believe they can put them close enough together that the dipole-dipole interaction, just the magnetic field, this was bothering us in our experiments measuring coherence. They think that they can make that strong enough, and then there are a bunch of lines to control it and things like that. So there are a bunch of ideas out there about how to deal with this. All right, so now let me switch gears a little bit. And I told you, I think, what are the good things about donors in silicon. Maybe what are some of the not so good things. But electron spins are good because they're small. So is there another system that we can do? And it's now that people by and large don't remember, but when Bill Clinton won the presidential election the first time, he had an advisor by the name of James Carville. And he had a famous statement, right? At that time, the economy wasn't good, so George Bush won, the father was president, and he was running against Bill Clinton, and the economy wasn't doing so great, and Carville's statement was, "It's the economy, stupid." So that's how Bill Clinton got elected, by telling everybody the economy was terrible. And what I would say is, let's change that. Materials. As Jason said, it's really hard to figure out how to do these materials. And so what we want to try and do is switch materials. So the physical system is a little different. What do? You take some liquid helium, you put a positive plate under here, negative up there, you inject some electrons, and it turns out the electrons float on the surface. All right? Helium is what's called a negative electron affinity material. It means electrons don't want to go in there. There's about a 1 eV barrier to push an electron into the helium, but it'll stick to the surface just fine, and it has a wave function and so forth. It turns out if you don't put much field down here, it sees its image charge in the helium, and it binds with about 3/4 of a millielectron volt, and the Z component of the wave function is just a radial hydrogenic. I mean, you can put it in, you just immediately get the radial hydrogenic equation. It's plane waves in X and Y. You can then make this binding as big as you want just by making that more positive. These things are incredibly mobile. Remember I said our best silicon things have a mobility of about 1.5 million. The absolute best 2D electron systems in gallium arsenide, I think it's either, is it 37.8 or 38.7 million, something like Lauren Pfeiffer grows these things. Here, it's just 100 million, a little over 100 million, right? It's just helium. There are not many things to disrupt the motion of the electron. It's also able to be used with very low density. People have worked with these things at densities of 10 to the 9, all the way down to about 10 to the 5 per square centimeter. About the lowest I know people have ever been able to do in a semiconductor in some special things that Lauren Pfeiffer made in gallium arsenide, they were able to get down to about, I think it was 2 10 to the 9, something like that. And if you think about it, 10 to the 8 is 1 per micron. So 10 to the 9 is 10 per square micron. That's sort of the densities that you would like your qubits to be, just so that you can control them. In fact, there are several different ways people have talked about building qubits. The first proposal, Phil Platzman and Mark Dickman, their argument was, well, these are hydrogenic wave functions, and now you look at it sort of on its side, and energy is going that way. You park 1 electron here, 1 electron here, and they can either be in the ground state or the first excited state. That is a charged qubit that probably has fairly short coherence. We've been interested in spin qubits. Dave Schuster had the idea, hey, let's just make a little puddle, well, a potential puddle, and we can move the electron back and forth, and you get a harmonic oscillator, but it isn't a perfect harmonic oscillator, it's anharmonic, and therefore we can make a qubit out of that. And it also couples very well to things like superconducting transmission lines, which is what Dave likes to play with. So I'm going to talk about the spin stuff. You can ask, okay, what do we know about spin coherence? And the answer is not much. We know in silicon germanium, this free 2D electron is about a microsecond. The phosphorus donor is 10 seconds. Now we have a free 2D electron on helium. What do we think T2 is? The best we can do is we can make some estimates. So here is sort of the picture. The idea is the electron is there and it's sort of fuzzy and it sort of touches these helium. And the way it's going to get a spin-orbit interaction, the way it's going to get this Rashba, is because that electron is going to have an amplitude to be in the 2p band of the helium, where there's a spin-orbit interaction. So to the extent, well, the 2p band is way up, EVs away, but there's going to be some amplitude up there. To get an idea of how much, you find some guys who've actually done an experiment. They didn't do an experiment on electrons at the surface, but if you take an electron and jam it into the surface hard enough, it goes inside the helium and it forms a bubble. Reason it forms a bubble is because the helium is closed shell, right? It doesn't want to, the wave functions don't want to overlap. They can't. Pauli exclusion says they can't. So what it does is push the helium atoms away, and you get a bubble in here that's about 15 angstroms in diameter. People have done experiments on those bubbles for 50 years. You can measure the energy levels and everything. But these guys did a spin resonance experiment, and what they could do is they could show that the shift in the G factor, they could put an upper limit. It was no more than 3 parts in 10 to the 7 away from the perfect free electron G, 2.0023 something another. Silicon, on the other hand, has a delta G over G of about a part in 1,000. And so now if you compare those two, those basically are going to tell you how big are the spin-orbit interactions, right? Because the way you shift the G is by mixing in some P-like character into your wave function. And that ends up coming in squared. So you expect about 7 orders of magnitude less decoherence for the electrons on the helium than in silicon. And since in silicon you can get a microsecond, it means on helium, a mobile electron should have a coherence of at least a second. We are trying very hard to measure it. It turns out you have a very low density of electrons. You have one surface. So trying to do the spin resonance and measure that turns out to be a quite difficult experiment. Okay, how do you do things? Well, you do a thing like this. You have your helium level down here, and remember helium's a superfluid, and it wicks up, and so now you have some channels. You cut channels. And so the depth of the helium is not defined by trying to level something or anything else. It's defined by the thickness of these layers, and so it's easy to make that well defined. And so in fact, you go to your friends who run a semiconductor company, or in this case, friends at Sandia National Lab who have a semiconductor fab, and they have a picture that shows all these nice things about transistors down here, and you say, yeah, that's cool, but I don't want any transistors. I just want silicon to be a substrate. What I want are a bunch of metal layers, and then we etch some holes, and so you make these channels up here, you put all this in a copper cell, you have a little bit of bulk helium down here, so it wicks around, fills up the channels, you have some UV up here, zinc film, you photoemit electrons into the vacuum, they settle down here, and you have electrons sitting on your chip. Hold that, it has to be superfluid. Here's what a chip looks like. This particular chip was 2 by 2 millimeters, and okay, you wire it up. And now what we're gonna do is we're gonna move electrons around, and we're gonna use what's called a charge coupled device, which probably you know. But the idea is we are gonna have what's called a 3-phase CCD. We're gonna start, this one's gonna be positive, and so if you look, the potential energy picture, the electron's there, and now we make the one next to him positive, and now there's, looks like that. And now we make this guy a little bit more negative, and so the electron drops down into that. And now we've moved one gate over, and you repeat that, and you repeat that, and now you've moved 1 pixel, right? So in your, you know, little cameras and things like that, when they talk about a pixel, if they're doing a 3-phase CCD, that's 1 pixel. Well, so the question is, what about, you know, you can do this in silicon. Well, so George Smith, he and Bill Boyle came up with the idea of a CCD, and he said that actually the idea of the CCD took them about an afternoon to think up. It was fairly obvious. People were making MOS devices, and you just did it. And then they made it, and it didn't work real well. And the problem is that you have traps in there. And now you're shifting these electrons along, and they're going along this surface between the silicon dioxide, and it runs into a trap, and it catches the electron, and it just gets eaten. All right? And so you start with a bunch of electrons on this end, and they never make it to that end. And he said what was hard, it took them a good week to figure out how to make what's called a buried channel CCD, which gets you around this to a large extent, but not perfectly. All right? And so defects can be a problem. The very best silicon CCDs operating at the optimal temperature, which is probably maybe minus 40 C or something, you can shift about 1 million shifts before all your electrons are gone. So if you start out with 1,000 electrons here, after about 1 million shifts, they're gone. They've all gotten trapped. Or maybe they get trapped and released later, but they aren't on the right pixel. They're back over here someplace. Okay, so we decided we were going to try and see how these worked. And so what we do is we have, these are the gate lines. These are our gate lines. These things are channels. So what you're seeing are 2 different layers of metal on that chip that the Sandia guys made for us. These channels are filled with helium. I guess I didn't, it's 3 microns wide here and 6 microns wide here. The 3 gates is a pixel, that's 9 microns. We would collect our electrons over here. We had what we called the door gate, which would keep electrons out. And we have a gate where we can sense them, we used, graduate student named this the twiddle gate. You twiddle the voltage and you move the electrons back and forth, and you pick up their charge with the sense gate. Now I should say, we don't, by and large, don't have single electrons. These sort of represent a little packet of electrons. We also had a vertical CCD, and we've shifted them that way, and we have little places we can store them and play games. But now what you do is you ask yourself, how well? So all you do is shift back and forth and back and forth and back and forth. And do all the guys' electrons come out in the right place? And the first time we did it, we had about 4 electrons in each packet. And okay, we shifted it once, 1 pixel, 1 million pixels, that's our 10 to the 6th, it's like a silicon CCD. We went out to 10 to the 9 pixels. We couldn't see any errors. Takes, at the rate we were going, that took about 70 minutes. That was defined by how long it took to go get dinner and come back. Another way to look at it is those electrons have gone 9 kilometers and nobody's gotten trapped. We then did it just on average 1 electron per channel, actually a little less. We have a whole bunch, 120 channels in parallel. We add them all up and measure them in parallel. But the end result is we can't see any evidence of electrons getting trapped, which if you think about it, right, traps are usually defects in the crystal lattice or something. It's kind of hard to have a defect in the surface of a superfluid. Okay, so now we want one electron though. We don't want a lot of electrons, and how do you get one of something? Well, you just narrow it down and use the fact that things repel one another. Electrons as well as sheep repel one another. And so you get one at a time coming out at the end. All right, and so here you get one sheep per cycle. We're going to try and get one electron per cycle. And this one looks then like this, where we have, again, by the way, all these little holes, this wasn't made at Sandia. This was an IBM process that we have no control over. And they put in all these little holes, I think probably to control stress in the metal layers. So these are metal layers. We wish these holes weren't there, but okay, we deal with it. We're going to collect electrons over here. Now, here's our channel. It starts out about 2.5 microns wide. It narrows down, and here it's 0.8 of a micron wide, about a micron deep. We deposit them in here, and then we're going to shift them down, and actually I think there's a little animation that sort of shows. So we put them there, and then we're going to take a bunch of electrons, and we're going to clock them, right? This is just a CCD. But now when it starts getting narrow, not all of them make it through, and we throw the rest away, send them back to the reservoir. And that, the student doing this, Micah, she estimated that we probably had 10 to 20 of electrons in that little packet. But now what she did was she brought that group of electrons into that region that's narrow, and there are 5 gates in there. And after she brought them in, she made the potential look like this. So they were all locked in. And then she raised the center and basically just split the packet in half. And now what you do is you take 1/2 and you send it back here, you sense it, and then you store it back here. The door stays closed at this point. In fact, the door stays closed the rest of the day. And we'll keep working with this same group of 10 or 20 electrons all day. And then you do it again. And you measure how many come off, and then you store them. And in the end, what happens to the last electron? Is it going to fall over to the left, or is it going to fall over to the right? Well, we can bias that a little bit. We can put on a little bias on one of the gates, and if the bias is low enough, it'll still 50-50 go left and right. But once you get to a high enough bias, and that depends on temperature and things like that, then it's always going to go one way. So that sets a minimum delta V. And then there's going to be a maximum delta V. What happens if you had 2 electrons? Well, I'm now going to change this bias. At first, because electrons repel one another, even though you raise that energy, they're still going to try and move away from each other because this thing's small. But at some point, that V is going to get large enough that they're both going to go that way. So that means there's a range of delta V's here, right, that is going to give you 1 electron. And so you go through that. Try and push the button to get it to go to the next one. Then you hit the screen. That always helps. And what do you get? So here is measuring that delta V, that offset voltage. And we saw a little glitch here, right? A little bit of a ledge. These are voltages measured down on the gates. Voltages that Micah applied at the gates. Actual voltages, potentials at the surface are a couple orders of magnitude smaller. So in fact, these steps turn out to be a few millivolts. And when she went back and measured more carefully right in that area, sure enough, these are in fact different days. There is really a ledge here where you get the same number each time. There was only one trouble, and that was, it wasn't 1 electron. We believe it's 2 electrons. That's my fault. I had convinced Micah that she ought to use a socket so that we could put the chip into a into a little thing and then put it into a socket in the helium system. The only trouble is the socket's made out of plastic, which we didn't think about. Plastic, when you start putting electrons down, it all charges up, right? Electrons go and stick on the plastic. And so they messed up the pattern of how the electrons went. And so in fact, what would happen, only part of the channels would get filled up. So it was a dumb idea I had that, well, these things happen. Okay, so that is about all I'm finishing up 2 minutes early maybe. Well, no, I have one more slide after this. So what I would argue is that electron spins, intrinsically, they have plenty of coherence. Coherence is not an issue. And, 1998, everybody was worried about, will spins in semiconductors have long enough coherence? The answer is yes. 1 and 2 qubit gates have been demonstrated using electrons in dots, which Jason has talked about, and bound to donors. They can be small and fast. Small, I think, is particularly important. And if you have 10 to the 9 qubits, they better operate fast. Otherwise, yeah, you may get an answer, but it may be your children get the answer. Individual devices people have done get very high fidelity. I guess I didn't give the numbers, but some of those single donor experiments, they can get fidelities of 99.9. As Jason was showing with quantum dots, he can get 99.7, these sorts of things. Scaling to a large computer, on the other hand, I think has a lot of big materials problems that have to be overcome. I would say that is true probably in any approach people are taking for quantum computing, right? We all like to ignore the materials things, but in fact, right, there's a reason why chips are made out of silicon and not germanium, even though the first transistors were germanium. And it all has to do with materials. And I guess what I would like to argue is that floating electrons on helium, I think we get some of the advantages. We can get basically the same sizes that spins in silicon have. Okay, they have a mass of 1. They have to be a little bit smaller than the silicon devices. It turns out it's not as bad as you might think, because you can apply remarkably high voltages to helium. It is one of the, and vacuum for that matter, they're really good insulators, better than, say, silicon germanium. And we think that those materials may be easier. But that's still, that's still in its infancy. One last thing. So everybody typically likes to talk about, there's this sort of race. Who is going to have the quantum computer first? Is it going to be trapped ions? Is it going to be superconducting qubits? Is it going to be spins in semiconductors? And I think we have to step back a little bit and think about it. So if we need, say, 200 million qubits, if you put in the numbers, it's 200 million inches from the steps of Nassau Hall to the Pacific Ocean. So we have to get from Princeton to the Pacific Ocean in terms of building this quantum computer. Where are we now? Well, we're about here. Okay? So a lot of people will say, well, I turns out to be ions, R turns out to be resonators. They have a huge lead, right? They got 3 times as many as this guy, or 5 times. Yeah, they haven't hit the Mississippi River yet, okay? Or a lot of other things that are along the way. And okay, nuclear spin NMR seems to have hit a brick wall. And the topological guys claim they have a shortcut and they're going some other direction. And the thing I would like to argue is that there's a lot of, there are companies getting involved and investing large amounts of money, and that's all good, except they're trying to pick winners and losers based on, they haven't even made it down the steps off Nassau Hall yet, let alone tried to get across the rest of the country. The problems in scaling are very non-trivial, right? It's not an accident that it took the semiconductor industry decades to learn how to make 10 to the 9 of something on a chip, right? It's a lot of material. So a lot of people like to say, oh, we're going to use silicon because that's what the semiconductor industry uses. It's utterly irrelevant, right? The semiconductor industry, its memory is 1,000 electrons. If they have a few defects, they don't care. And in fact, modern chips probably have more defects at the silicon-silicon dioxide interface than the ones years ago, just because the kinds of processing techniques you have to use to make these very small transistors introduce defects, but they're irrelevant. They're working at room temperature. They have lots of electrons. They don't care. This is a different world that now a bit is 1 electron. And I don't think that just saying, oh, well, the semiconductor industry knows how to make 10 to the 9. Therefore, once we demonstrate a qubit, they can make 10 to the 9 qubits. I wish it were that simple. Maybe it will be. That would be great. Then we'll all have quantum computers on our, well, we'll keep them in our fridge. But everybody will have a delusion refrigerator in their kitchen. But I will, I guess, leave it at this. Thanks. Questions? There've got to be some questions. Either that or you're really desperate to get out of here. After 4 days, I could understand that. All right.
Well, if there are no more questions, we do one. We have a little
I get a goodie bag.
speaker on
Thank
behalf
you.
of the organizing committee. So yeah, let's thank the speaker for the inspiring. And before you all go, everybody should have gotten an email this morning about a small feedback survey. And it would be very important if you could fill that, because as you know, the school is organized by grad students who are like not professionals. So feedback is very important for next year's organizers. So thank you all for coming, and hopefully see you next year.
I figured we could end Thank you. So what fraction? When did people come to the
I will send you the form after.
So,
Oh, yeah, okay, sure.
But then some people don't show up.
Then there's something to catch you. Sorry. Yeah. What's the farthest away?
Yeah,
very smart.
yeah, I have to know, like, the failure.
No, I met a couple.
Do you all want to meet for dinner? Oh wait, a lot of you are leaving like today, right?
I'm not.
You're not. Is anybody else here today? Tonight?
Okay.
I am sort of around, but I have some plans already, so
Oh, okay.
I don't know if I'd be available or not.
When are you
All right.
leaving?
Good.
You're around for dinner?
Yeah,
Yeah, we should meet somewhere.
I don't know how to get a hold of you guys.
We
Oh
have.
yeah, here comes the group chat. I will.